All right, looks like we're finally going to finish off the Hamiltonian section of the code book. Yeah, so let's just get right into it, I guess. The first thing we're doing is implementing this householder transformation, which looks very similar to the Grover's diffusion operator, but also I'm pretty sure it says, right, numpy.outer you will find helpful, but I'm pretty sure I looked into this before, or maybe it's inner. One of them doesn't work well with complex numbers, so let's find out. I guess it was inner. I was sworn it was outer. Maybe they changed it. I don't remember. Yeah, I guess. I mean, I could probably go back and look at the video. All right. It's a householder transformation. I've never heard of this before. Am I just like out of the know? Do I really know nothing about this stuff? Oh. Okay, I thought it was like a specific quantum thing. It's just a linear algebra thing. Okay, well, that explains why. Yeah, I don't know anything about math, so it's good. Implement the prepare oracle using the householder transformation. This is available from the previous exercise. For simplicity, this means that our auxiliary register will have k qubits and state 0 is the all-zero state. Okay. So we have so I think what we want is we want whatever this function is called, householder. And then we want the function to call the state, which is simply the 0 minus alpha list. I think, yeah, alpha list. Let's say this is divided by the absolute value. Oh, no, that's confusing. It's the normalized. Version of it. At least I'm pretty sure it is. Let's try it out. I don't think it's just divided by the absolute value. Yeah, that's what I thought. So we want to pretty sure there's a numpy function. What are the odds that this is it? No, it's not. Oh, that is what we want. Normalized vector. I should have done this. Normalized vector. Let's see if I can print things in this. No, of course not. What am I doing wrong here? Do we have to apply it to something? No, I don't think so. I think we just implement it. 0 minus alpha over the normalizing. This is unfortunate. I really do not want to open up. Maybe I should be less hesitant too, but I don't want to open up the code editor again and actually plug this in. Yeah, this is kind of a pain. But I do not understand what I'm doing wrong. 0 minus alpha, this is difference of states. Then 0 minus, oh, no, that's 0 minus alpha. Why does it not let me simply print? This is the most annoying thing. Guess I will now open up and go to my documents, and I already have this set up, so I guess don't need to import numpy. I can just open up a all right, now I will add this to the there we go. Now this is visible. Okay. Now we will copy over our code from here. And then we will copy over our code from here. And then we will say print prepare what is our alpha list? Let's just do a random numpy dot random uniform 0. Actually, here I'll do this so it's easier to be seen. On import import star. I haven't saved it yet. That is why I did that. And then we are going to redo that actually. And we're going to do import p. Then we're going to. I think I have to restart my Python console. All right. Guess we should probably actually make sure that this vector is Okay, now we can do or actually dot alpha, and it's 1. Okay, so we ensured that it's normalized. Now we're gonna do check to make sure this is unitary p p. Okay, yeah, so it's the identity. So we made a unitary matrix, but it isn't the one that they want. This is very excellent fun here. Truly, I do not know why this has happened every time in the Hamiltonian one. Let us see, 6H7, H7.2. Is this Q-reg again? That person was having the same troubles I had last time. And that person did what I did as well. Okay. We already passed that question. All right. Very helpful. But what was the hint? Over here. The hint was check the top of the H7 codes and take a look at how the A is defined in terms of vector elements. Once again, I'm not reading. A list of coefficients. Your answer is quite close. I recommend to check the top of the H7 code side. Then, all right. Let's see. We expect the following behavior. We're doing prepare. Where alpha is prepare the square root. See, like, this is so if alpha is a set of, it's a vector, right? Then alpha j has meaning here, but we're taking the square root of a vector here. I do not, is that element wise? Like, that, I don't understand what that means. Or is that supposed to be the length? Like, is this say 3, right? Which is very inconvenient. Fine, I will take the square root of, if that is what it wants. It does not want that. Oh, does it have to be greater? Why? I feel like I'm missing something here. Okay, so the last node, whatever. For a linear combination of unitaries, is alpha sub j times u of j with alpha sub j greater than equal will define, prepare, and select as oracles. So do they just have to be greater than 0? That's the wrong one. Okay, also this indicates to me that bad operand type for abs, this isn't an array, it's a list. They say it returns array, but that's a NumPy data type, but bad operand, this has to be a list. Which is funny because that means also that their input, right, this is a list. This is not an array, so it's fine, but you know. Okay. Okay, so prepare of 0, which is what we're doing. Takes are we supposed to really? That's one that isn't clear that this is the norm, right? You have, if, for example, if I go to there's different, here we go, right? You have 2 and then you indicate the norm order, I guess. So you can have L2 norm, right? L infinity norm. So that is not, this is not clear that that is what I was supposed to do, that we had, see, 1, this is a vector, so 1 over square root of vector, I just interpreted that as the norm, but I don't think I've seen that anywhere else. And then the square, this is just, why? Why? And I can't print anything. And this wasn't a list. This was an array. Okay. Moving on. Okay, what are we doing? All right. Implement the LCU and the select oracle. Okay, so what we want to do is we want to probably call prepare alpha this, then we want to call, oh, but we should do dot qubit unitary prepare writers equal auxiliary. Oh, sorry. Yeah, auxiliary, and then we want to do select u list, and we want to do the same thing, but we want to do the adjoint version of it. Then adjoint. Oopsies. There we go. Finally, that one makes sense. Now consider this combination of unitaries. Okay. Do I have to actually pay attention to that? No. Okay, wait, maybe I do. Oh, no, I don't. We just need to LCU, LCU, alpha, list, U, list. Okay, wait, maybe I do need to pay attention. Okay. Okay, finally consider. Oh, to state 1, 1. That's also probably why. L dot x. Or we'll do main q poly x equal I. There we go. I was correct. I did not need to pay attention to what that was. We now know prepare and select, but it turns out that we can also use them to implement memory. Okay. Use the prepare and select procedure you find above to generate superpositions of the 2-qubit basis state. Okay. Let me remind myself of what select does. Okay, well, I'm going to do, I think I just need prepare right now. Qubit unitary prepare data this is equal 1. Then we want to select I think this is what select. I forget what select function does. Yeah. There we go. Let's see, what does prepare do? Okay, I'm gonna just comment this out for now. Okay, so it produces the state. Okay, what's oh, is this because this has to be oh, whoopsies. Oh, main is not defined. Let me just see how many qubits there are. Oh, there. Wait. It doesn't. Is it still 4 qubits? I'm so confused right now. Yeah, I think there are 4 qubits. Okay, this was not clear that. Well, maybe it was clear. I should be critical because I didn't read it. So, be honest, you know. Okay. Maybe I should actually read it. Or beta greater than equal with beta squared LCU equals, let's see, prepare okay, so I should do first I should do beta squared. Make sure that's right. This should also be okay, and then we will have where selects inputs the, oh, I see. Select J. All right, so this will input U sub J on B. So I think this is what we want. Let's see. Let's see what's going on here. What even is? Oh, whoopsies. All right, measurement process. Let's see. See, there's 4 to 4, 16, and X, Y. Is this gonna work? Measurement process. I don't know what a measurement process is. Ah. Measurement process. Okay. What does it return? I don't know what a measurement process is, so. Um, I don't understand why this isn't just being the output of of what it is, right? We have This is let me do this again. Okay, whatever. I don't. Okay, let's think about this a little. Auxiliary states J of A are used to store memory addresses to main D prepared from some initial state 0 by acting with the unitary so we want to, maybe this should be oh my gosh, I really okay, there we go. So now it's in state 0, 0 plus. So it's just looking at these last four. So in order to remember which data belongs to bear, they must remain correlated with addresses. So our task is to take the initial state 0A, 0D. So this is the auxiliary, this is the data to this form, that form. Which, right, so, okay. Here's why I'm confused as to what U is in this context. Let's see. Okay, so up here we have select, which I'm just going to call S of state J, state B equals J use of J of B psi, sorry. Then we have P of 0 equals 1 over alpha square root of alpha minus J. This is also really annoying that prepare is a function of, right? Prepare has like there's some alpha specified that's not as input, or some U of J here that's sort of like globally defined. Now if we scroll down here, we see we want the state beta equals beta J. It's a really terrible J, I know. J auxiliary D subject, whatever. Doesn't really matter. Okay, so what I'm saying is this, right? If we just do this operation, we see, okay, how do we get here? We do prepare. So now we have prepare maps us to whatever alpha is, where alpha is alpha is beta squared. So yeah, so we have, in this case, beta squared, which is square root times, oh, is that what it needs to do? Do I have to say, also I'm just going to make this passive anyway. Do we say beta is equals NumPy? The square root of 1 is 1, so I'm just going to say equals divide equals NumPy, and then norm. Is that the problem that we're encountering here? Let me go check prepare. No, we normalize it there. So we normalize the vector here, and then we map it correctly, right? So now we have 1 over square root of betas, which is whatever. We can just ignore that. Then we have, I really can't expand this at all. Then we have, I will just open it. Okay, this was a mistake to use this online site. Then we have, beta times j. That's what this did. So then, now that we have beta times j, we want to select so that we can create j of let me see what select does. Select takes that and applies that unitary. Does this even change? Oh, am I even changing anything with this if I did? I'm so strange that nothing changes with this. Yeah, I don't understand how none of the outputs are changing. Yeah, okay. Okay, what is going on here? Okay, here we can see it down here. Oh no, that's just, yeah, select prepare 0D. Hmm. See, my question is basically just, oh, do I really need to do? I think cool, but that's okay. Actually, maybe not. I don't remember if I need to do this or not. Yeah, no, it just undoes the operation. How is select just not doing anything? Probably because, yeah, so this is the state that prepare makes. Regardless of if I square it or not, which makes sense, but I'll square it anyway. So then we have select, which takes I did not even know you could do this in NumPy, but does the controlled unitary of that associated index. Control wires are those two main wires. Control string is this. And we know k bits is 2. Oh, I know why C naught does nothing. I know why I does nothing. So this is 0, 1, 2. Let's see, this is 16, 15, 14, 13, 12. 15, 14, 13, 12. Which means, let's just do a new one. Let's do 12. And the 4 qubit system is 8, 4, 0, 0. The 0 is 0, 0, 0, 0. Oh, okay, okay. So we have now this state that we want to, right? We have 0 plus 12. We want to map it over and prepare. Okay, that I guess that kind of makes sense. So then, wow, this has been 45 minutes. This is very painful. Let's go back over here. So then what can we do to see the only ones that are going to trigger if we have this 1, 0, or this 1, 1 state and the 0, 0 state are the first one and the last one, right? If we're thinking of the strings that will trigger, will be 0, 0, 0, 1 won't, and 1, 0 won't. Yeah, so right now this is the equal probable, which is good because we have, which is fine. So now we want to map this over. So if these are true, what operation do we want to do on this qubit? We want to say, okay, we want to create from the 0, 0 state, we want to create the HC0 gate. So on the first one, okay, so here's what I'm thinking. I'm thinking the inner two don't matter. We want Kronecker product of QML dot Hadamard dot matrix followed by the identity. Then we want the C0 gate. All right, that has changed something. Let's think about what this would do. So we already have established that our state coming into it is 0, 0, 0, 0 plus 1, 1, 0, 0. And then select will go through and generate the control string, which is 0, 0, 0, 1, 1, 0, 1, 1. So now we just have 0, 0, which triggers. And on that event, we have a controlled Hadamard. Yes, and then we have at the end, we have a controlled C not. And then do we need to, let me see what happens if we undo operations. All right, so this is fine. I'm just trying to understand how the state gets created. So if we have this, okay, so then in this case, this becomes H. Well, maybe we want bell equals let's see, do we want oh, there we go. Oh, what is bell? Oh, that's that shouldn't even be there. I just forgot to copy it over. All right, print bell. All right, that's fine. I want to try this. All right. So here's what should be happening. It's going to, this is simply a controlled bell state. Oh, let me actually put it in both of these. Let me also try this. Okay. So it will go through. Okay, I'm gonna look at this. Maybe they asked a question. Oh, they did. They did ask a good question. Oh, so this is just CZ, CX, XZ, XX. Okay, what am I missing here? Yeah, so they must be squared. I got that. Maybe I should specify box. I can also delete these, clean up my code just a little bit. And then I want to, okay, so I've been interpreting this unitary entirely wrong. Unfortunate, but so let's see if we have, which I started to realize once I actually started to draw out the circuit and understand the superposition. So we have CZ. I guess this is just, is there any non-painful way to write this out? We have ZZ, XZ, sorry, Z, X, X, Z, X, X. And that's, I'm going to test something now. I'll test their little UL poly matrix matrix. Here's what I want to try out. Okay, so I'm getting the right, let me check before I say that. I'm getting the right answers right now. The amplitudes on the main register are proportional to 0, 0, whatever, right? But now I'm not getting the right answer. So I think maybe this does actually matter. What I was going to say is for this beta list, I don't think these inner ones matter. I think my focus was too heavily on that I really threw myself off this entire hour. Okay, yeah. So my problem was that I was hyper focusing on this beta list when that's not what they were judging it on. Which is very unfortunate. And then when I finally realized enough to draw it out, I realized my unitaries were messed up. But I was still, yeah, I was still very... Let me go through this actually. So if we have... These ones don't matter. And here, so if we have ZZ, then we map this to the now 0, 0. In this case, we have... This doesn't do anything, right? 0, 0 state. Oh, I didn't even need the ZZs, I'm pretty sure. Then we have plus whatever, then we have 1, 1, which then flips this to 1, 1, right? That's all my problem was. Wow, I was really overthinking that. Hopefully that's clear now, is that this was the two states, the two auxiliary states, and then this is what we needed to control. So right, 0, 0, if there's different betas, this would matter. But in this case, this is the only one that mattered for that beta list. Wow. That took a while.